Okay. Now we are streaming. And now we can start the lecture. As I was telling you, today we will go onto the other way concerning the resolution of our model. We have seen in the model of yesterday, the Moneris model, modeling nutrient emission into river system. How is it possible to build with an holistic approach a model for a very complex, complicated system like the catchment of the Po River, that is one of the largest rivers in Europe, one of the, I think it is the fourth or fifth largest river in Europe. Nothing comparable with what you have in Africa, of course. We have, as you may remember from the lecture of yesterday, we have discharges on the ranges of 1,500 cubic meters, but on African scale is nothing, but on a European scale is significant. The point is that with the application I have discussed yesterday, we have seen how it is possible with these holistic approaches to have management models, in this case river management models, that allow us to decide or to choose among different management strategies of ecosystem. In the case we discussed yesterday, the ecosystem was on an ecological scale, ecological processes scale, so large scale, very large. I recall you that the catchment we were modeling yesterday is around 70,000 square kilometers, so very large river catchment, so with very heterogeneous conditions. And we have seen, but even if a system is so complicated, complex and heterogeneous, with our holistic approach, we may gather some information concerning the most appropriate strategies to manage such complex system. So yesterday we introduced a model on a very large spatial and temporal scale. I recall you that the spatial scale was that of the subcatchment, so we are talking about tenths of square kilometers, 10, 20, 30 tenths of square kilometers, while the temporal scale was yearly. So the model Moneris we have described yesterday had a temporal scale of on a yearly scale, and in particular the application we have shown yesterday was calibrated on a 5-year time range. On the contrary, what we will discuss today, it is a completely reverse from the scale point of view approach. In this case, today we will introduce fish growth models. So these models that we may employ for describing higher trophic levels. So in particular, we study with these models the interaction between algae and or zooplankton and fish, because you know that fishes feed on algae and or on zooplankton. And we will build this model as always by basing on the energy conservation principle, so continuity equations. And we will build this model by having a different approach, in particular by looking at the fate of the food consumed by the organism. As you will see, we will end up with a very classical example, a very classical ecological model, that is the Ursi model for metabolic growth. And as you will see, with this model, it is a generalization of the logistic growth model that we have seen in the beginning of the class when we introduced the first model for bacterial growth. But as we showed, we ended up with a logistic model that describes limited growth. In order to build this fish growth model, we shall start by observing that growth depends on species-specific characteristics, but also on environmental factors. So fish species-specific characteristics and environmental factors as well. These factors are, for example, the age of the fish or environmental conditions like the environmental temperature, as we have seen and as we have said several times in the class. Temperature is a very important forcing function for all ecological models, or other species-specific characteristics like the ratio of food ingested, so how much food is available, or other species-specific characteristics like the body size. As I anticipated, historically, the first empirical models that were employed to describe metabolic growth were the logistic growth model. Logistic model, that is a model describing limited growth that ends up in a sigmoidal curve in which you have the population dynamics described in time by curves like these ones. So we have a kind of saturation behavior while times gone. So we have a growth population that is growing up to a certain limit that we have learned to call this limit carrying capacity. So by employing the logistic model, we are including into our description the fact that growth is not unlimited. Unlimited growth is biological nonsense. If you want to build a significant or a meaningful biological model describing growth, you have to include some kind of limiting effects, so that the most general way for describing this is that of employing a sigmoidal curve or saturation curve in which the population growth tends to a limit that is called the carrying capacity of the system. There are other flavors of the logistic growth model, like the Gompers, von Bertalanffy, and Ritter models, that are all models we will discuss today or shortly introduce today. The point or the methodology, the methodological approach or epistemological approach in this case is that of finding the best fit. So we have mathematical models in which we have some parameters but do not have a precise biological meaning, not necessarily, but as we will see in some cases, it is helpful to introduce parameter with a sound biological meaning. But the idea is that we introduce some kind of mathematical description in terms of differential equations or mathematical model, or we introduce the characteristics of the system as we have discussed in the latest lectures. And we simply look for a best fit. So we look for a calibration of this model by changing the parameters, but in principle do not have precise biological meaning, with the scope of finding a best fit between the results produced by the model, the mathematical model, and the results that come from observation of a real system. It is a matter of calibration. Let's give a look more in detail to the factors affecting fish growth. Now we are focusing much more specifically on the organism, a fish. This is an example, and as we will see by the end of this lecture, this approach is totally general. So we do not need, this model is not only applicable to fish, but it is applicable to a large class of biological systems. In particular, those systems are growing systems in which growth is affected by two classes of factors: intrinsic and extrinsic factor. Intrinsic factor refer to the species, to the race, to dimensions or swimming activity, maturity, or age of the animal or of the organism we are looking at, with factors that are intrinsic to the specific organism we want to model. And then there are several extrinsic factors that are very relevant. We may, in turn, classify these factors into two general classes: abiotic and biotic factor. Abiotic factor are factors related to the conditions, surrounding conditions in which the ecosystem or the living system I'm studying is embedded in particular, for example, photoperiod, how much light. Now you know how to model photoperiod because we have introduced last week, or sorry, on Monday, the first model describing photoperiod. It is an astronomical model, of course. The temperature, and we will see how to introduce temperature in our models, in particular when we will discuss algal growth models or primary production models, but it will be the subject of tomorrow's lecture. Oxygen content, because we know that oxygen is a very important element that changes or influences significantly the performance of living system. pH condition, again, pH regulates the equilibrium constant of several biochemical reactions. Presence of other gases or of other elements like carbon dioxide or toxic substances, or the quantity of salt, so salinity, and light intensity. And as we will discuss, I think Friday, light intensity is also a factor that has to be modeled in order to include the effect of surrounding environment on the process of primary production. Biotic factors that are extrinsic in this case are related to diet, ration, feeding frequency, parental care, diseases, presences of diseases, or other factors related to population dynamic, like, for example, social hierarchy. So you see, diet is what the animal eats, ration is how much of what the animal eats is available per day, feeding frequency is how much the animal or the organism is feeding, parental care, diseases, and social hierarchy instead are factors, extrinsic biotic factors related to the condition in which the population we are studying is found. So, for example, there are populations of organisms that are able to perform services like parental care. This is the case, for example, of mammals, as we are. As you know, parental care is a substantial, fundamental factor, but it is driving the ability of a population, or it is fostering the ability of a population to survive against a terribly perturbated environment. How do we build these models? As I introduced, a metabolic growth model essentially is built by describing the fate of consumed food. The units of the model, so the currency may be that of mass or energy, and by now you shouldn't be surprised that we can employ these two currency alternatively, because we have seen that there are conversion factors that allow us to change between mass and energy currency by employing, for example, a quantity of different types of biomolecules like lipids, proteins, carbohydrates, and so on, that make up the body of larger organisms. So we choose currency, that might be mass or energy. And then we introduce some state variables, for example, consumed food, capital C, of this consumed food, so that is the food that enters into the organisms. This food, a part of this food is immediately lost in feces, so it is not assimilated. What it remains, it is assimilated material, so it's food that enters into a chains of chemical transformation that makes this food available for building biomasses of the organisms. Of the assimilated material, a quota is immediately lost by what is called specific dynamic action, SDA, that is the energy used for digestion from one side, and energy, a part of the energy that is excreted by urine or gills, or it remains after digestion, so after transformation of the assimilated food into organic materials, is what is called metabolizable materials, or materials that can go through the chains of the metabolic consumption processes. Of this metabolizable material, a quota is immediately lost for various activities like swimming, hunting, and so on. This is the energy lost for surviving activities. An energy is immediately, a quota of this energy is immediately lost as basal metabolism. You may recall that we have introduced the concept of metabolism that is subdivided into two quota, catabolism and anabolism. We have said that catabolism is the quantity of energy that is employed by a starving animal. So it is a quantity of the energy that is needed for maintaining the living machinery running. So this is basal metabolism. And what it remains after all this is anabolism, or the growth. So the quantity of the consumed food, but after all this conversion or all these consumption processes is left for growth. Again, we have a continuity equation, so we may write an energetic balance by, for example, writing that anabolism, or the growth in biomass of the organism, is equal to what goes in, consumed food, minus what goes out in various forms, like, for example, feces, or urines, or what is called respiration. In general, into respiration, we include the basal metabolism RS, the specific dynamic action RT, that is the energy employed for the digestion of the food, and the energy that is lost for other, or consumed for other living activities, like, for example, hunting, swimming, mating, building nests, and so on. So you see what we have done here? Sorry, by the application of a continuity equation, or energy conservation principle, is the first model in which we balance, we write anabolism, so fish grows in function, as a function of the consumed food and of the consumed energy due to the living processes. Nothing very impressive, nothing terribly new, but let us now translate this conceptualization to a mathematical model. So the general model, as you may imagine, as I introduced, may be written as anabolism, so, or growth, if you want, is equal to metabolism, or energy consumed per unit time unit biomass, minus catabolism, that is energy consumed per unit time, per unit biomass by starving organisms. So this is the energy consumed for maintaining the organism living. If we introduce a new state variable W, the fish weight, describing the fish weight, we may write, as is customary, that the variation in time of fish weight is equal to an increasing term, what goes in, positive terms, minus a subtractive terms, what goes out. So this is always this classical approach of converting the continuity equation by subdividing it into two terms, an additive term positive and a subtractive negative terms. W may be expressed typically in dry weight, so you will have the dw PEDX on the weight if we are measuring weights in dry weight, or it may be measured in wet weight, depending on the type of the organisms and type of data
Allô,
you have at hand.
allô. Ah, bonjour, tonton, c'est Jules.
Okay, sorry. Please close your microphones. The very basic assumption, very assumption, but is introduced in building this model is that the ingested food, so what it is, comes in, and the fish itself, so what you will have in weight, W, have approximately the same chemical composition. I use the sentence, we are what we eat, for remembering this assumption. We are what we eat. This means that the biomass that is produced as a consequence of the anabolic process, anabolism or growth, has essentially the same composition of the food that is assimilated by the organism. As you may feel that this assumption is very strong, in reality it is not so strong, because by now we know that all biomolecules or biomass in general have all more or less the same composition. We have a series of stoichiometric coefficients that are constant for all the biomolecules that make up the biomass in the biosphere, so in the living sphere, in the sphere of living things. So we are what we eat, and we need to do this assumption, otherwise we wouldn't be able to write such a balance equation. You remember, in order to make a calculation or arithmetic calculation about including or involving variables describing quantities that should be comparable. In order for this equation to be written, I need to be sure that we are comparing or we are dealing with the same kind of things. When I'm writing this equation, I'm implicitly or I'm accepting that the biomass that I'm describing has the same chemical composition, essentially, of the food that the biomass is built on. So the first approximation, the first assumption of the metabolic growth model is we are what we eat. So remember, because this is one of the questions, I may pose on the metabolic growth model. First questions. First, what are the assumptions for building metabolic growth model, the first assumption is we are what we eat. So that we can write this equation and being sure that we can subtract from the food intake to what goes out, and this is comparable to the biomass produced by anabolic processes. Now, let's see how we can mathematically formalize this conceptual model. So the variation in time of the weight of a fish is equal to what goes in minus what goes out. What goes in may be described by a function of a time, so CDT describing the consumed food, and the output may be subdivided into three contributions. So what it is taken away from the available quota of energy, available quota for growth, is the energy. We always indicate it like a W, this may be energy or biomass. So the second assumption of the metabolic growth model is that we can easily convert from energy to biomass due to the fact that we have coefficients that allows us to convert the quantity of biomass into energy as a consequence of its energetic content. We have seen some tables last week about that. The other term that we are subtracting, it is the feeding. So the first term, sorry, it is a quantity of energy or biomass of food, if you want, due to basal metabolism. So this is a fasting organism, so the energy consumed by an organism that is starving, it is not having any food available, plus the energy consumed by an organism that instead is feeding. This is the specific dynamic action and all the energy included into the process of getting food and digesting this food in order to convert it into metabolizable material. And then a last term that includes all the losses due to the fact that the process of transformation is not perfect. So you have feces, you have urine, you have excretion, you have temperature regulation mechanisms that, for example, may consume some of this energy. And so this energy shall be subtracted to what it enters into the animals. So now we are left with the problem of estimating these three factors, fasting, feeding, and non-digesting energies, as a function of the consumed food, CDT. Okay, how do we explicitate this? First of all, we shall model. So now we are introducing the mathematical, we are now really mathematically formalizing our conceptual model. For example, how can we model ingested food? Ingested food may be modeled as a function of time to constant f, the feeding level, and h, that is a calibration coefficient for your model, times the weight of a fish elevated to a power m. So in this case, the assumption we make of ingested food is that the feeding level describes the ability in that specific environmental condition of that animal to convert food into biomass. So you will have the topmost feeding level when F is 1, and you will have a starving organisms, so an organism that is not feeding when F is 0. Again, we include another constant, a generalization constant, and the very strong assumption in this description or in this model of ingested food is that the food absorbing surface is somehow proportional to the dimension of the organism. It is not a linear proportion, it is proportional to a quantity describing the dimension of the organism, that may be the weight of the organism itself. The proportion is not linear. Instead, the proportion is toward an exponential function of the weight of the organism. We can write this assumption because we know that the food absorbing surface, that is the surface of the stomach and then subsequently in the intestine, are somehow proportional to the dimension of the organism. The most general way of formalizing mathematically this proportionality is that of writing that the ingested food is equal to 2 coefficients multiplied by a power of the weight of the organisms itself. So this has to do with the ingested food. Now let's look at the other 3 terms, the subtractive terms. The first term, that one of fasting catabolism, may be modeled by using a function of the weight of or if you want, the energy or the mass employed for fasting activities is proportional again to the weight of a fish through a constant of proportionality that is called the coefficient of fasting catabolism. Again, here we have some kind of assumption that are of biological type or ecological type, in which we assume that the fasting catabolism coefficient is again proportional to the dimension of the organism. Again, for generality, this proportion is not a linear proportion. Instead, the proportionality is throughout a power of the weight of the fish with a different exponent n now. So we may write that fasting catabolism is equal to k times the weight of the fish itself. So, what are the assumptions we are playing here? The first assumption is that we are what we eat, so the chemical composition of food is very similar to the chemical composition of the biomass. Then we are assuming that terms describing energy consumptions are proportional, for example, to a quantity describing the size of the animal. So the terms describing energy consumption is related to the size of the animal. The largest the animal, the highest will be the energy consumption. This is the idea. We come to this conclusion by observing that in all over organisms that are able to digest materials in order to have metabolizable material ready for anabolic processes, in all these cases, in particular for these organisms that digest, the surface of the digestive trait is somehow proportional to the weight of the organism. So then let's go to the feeding. We have seen that we can model ingested food as a function of the weight of the fish, but of the ingested food, that the quota that is employed for feeding, it is only a part. We describe this by reducing the ingested food oxidity. So we reduce the consumed food acidity by a factor beta. Beta is again a function that actually takes into account the fraction of the consumed food that is employed that is finally ingested. So as we have seen in our first model, in our first description, we have seen that of the consumed of the consumed food, only a quota is transformed into assimilated material, and this quota part is reduced by losses, so that we can write that the feeding metabolism quota is equal to alpha, that is the fraction of the food intake that is used for specific dynamic action, so for the digestion activities, reduced further by a coefficient beta that describe the fact that not all of the consumed food is actually ingested. Instead, some of this quota is immediately lost due to losses in the process of consumption. And then we multiply this to the consumed food. So how do we weigh, how do we estimate the catabolism of specific dynamic action? We make it depend on the food consumed, that is different from the ingested food. So the food consumed reduced by beta, so on the ingested food, reduced by alpha, that is the fraction of that food that is employed for digestion or specific dynamic action. And then for all the rest, the quota of energy that is not digested and lost, we simply close the balance by observing that if beta is the function actually taken of the food consumed, so 1 minus beta, beta is in the range 0, 1, 1 minus beta is the quantity of food that is simply non-digested. So we multiply the consumed XCT food by 1 minus beta. So by what? That quota that is not digested. If we put all these things together, we start from our model, variation in time of the weight of the animal, what goes in minus what goes out, energy consumption, so energy conservation, continuity equation, balance. Ingested food is modeled as a function of the weight of the organisms through these two coefficients, and the function is not linear. Instead, it depends from an exponential of the weight of the fish. The fasting catabolism, as we have seen, may be modeled as depending again on the weight of the fish, due to the fact that respiration activities are proportional to the dimension of the organism, so the energy consumed by a starving organism is anyhow proportional to the weight of the organism. This proportion is not linear, but instead it depends from an exponential of the weight of the fish. We have two different exponential, m here and n here. If we include that we ingested food, so of the consumed food, of the ingested food, only a quota that is taken into account by beta is that is digested, so it is converted into metabolizable material. Of this, the non-digested quota is 1 minus beta, and for the catabolism of specific dynamic action, then we may describe the feeding energy, so energy consumed by feeding organisms, by reducing the digested food, beta times XCDT, by a factor alpha, that takes into account what some of this energy has been employed for digesting the food. So for converting, the bioorganic molecules that are into the food into metabolizable material. You may recall that as we have discussed the consumption processes, typically during respiration processes, there is a conversion of um, the energy stored into bioorganic molecules into very precious molecules that deliver into the organism energy that are I don't remember now the name of what molecule. Okay, you can just go back to look at the classes, the courses when we describe production and consumption processes. Adenosine, okay. We put all this together and we end up into this mathematical model that is a first order non-linear differential equation. First order because we have only derivative of time, first order derivative of time of the biomass of a fish. This first order derivative is made equal to a series of coefficients times the weight of the fish elevated to power n minus a negative subtractive quantity that is proportional again to the weight of the fish, and that is employed to describe the fact that growth is limited, so that a specific system has a well-defined carrying capacity for different types of living organisms. In order to model the effect of a carrying capacity or of a growth limitation, you have to include a subtractive term. And as we have seen in our description before, the subtractive term is made proportional to the weight of a fish elevated to a power n. Okay. If alpha, beta, f, and h may be considered approximately constant, so we may cluster all these constants into two macro constants that include all the heterogeneity and all the different factors that we have used in order to build this model, so that we may write that variation in time of a fish is equal to a capital H collective constant times an exponential of the weight of a fish minus a K constant, collective constant, times again an exponential of the weight of the fish. This is the well-known, very famous Ursin metabolic model. The Ursin metabolic model is a model we have obtained by some very general assumption on the food consumption. The first assumption is we are what we eat. The second assumption, we can easily switch between biomass and energy because we have constant conversion coefficients between biomass and energy due to the stoichiometric, to the fixed stoichiometry of biological matter. So with this assumption and some less, if you want, some more specific assumption concerning, for example, the absorbing surface of the digestive tract, like it is proportional to the weight of the organism, or to the quantity of energy employed for the basal metabolism, that is again somehow proportional to the dimension of the organism. All these approximation or all this assumption drives us to the Ursin metabolic model. It is a very important generalization of the logistic growth model. In particular, if we start to analyze this model, we may immediately find two completely different conditions concerning the relative values of exponent m and n. In the case in which we have what the exponent m is smaller than n, in this case, we have a limited growth model. So the solution, Wt of this differential first order nonlinear differential equation, is a sigmoidal curve, like was in the case of the logistic growth model. The sigmoidal curve, it is a curve in which you have an increase in the weight of the organisms. This increase goes through a point of inflection, that is the maximum growth rate. That happens when you have an inversion of the concavity of a curve. So this is the place where the second order derivative in time of the weight is 0. So this is a point in which there is a change in the concavity of a curve. And then if time increases, in the case m smaller than n, you end up with an asymptotic weight at infinite, an asymptotic weight that is representing the carrying capacity of the system. The asymptotic weight may be calculated on the basis of the two constants, h and k, while the inflection point is calculated on the basis of the asymptotic weight and on the relative difference of the exponents of these two contributions, of the positive and the negative contribution. The reverse case, we have the reverse case when we have that m is larger than n. In the reverse case, we have an exponential growth. And I just want to make you remark that this part of the exponential growth, it is somehow similar to the beginning of the sigmoidal shape or to the sigmoidal curve. So that we may say that this approximation, the approximation in which we have an explosive growth, it is applicable only on the early stages of growth, when the organism tends to grow after the maximum growth rate, so the inflection point, then there is a slowing down of the growth rate, so that the weight tends of the organism tends to an asymptotic value, that is W infinity, so that we may say that the Ursin model, the Ursin metabolic model, may describe the early growth stages, and in these cases you will have that m is larger than n, and then when the organism is growing, you will have a switch in which the limiting effect or the limiting effect of the negative part of the continuity equation becomes predominant. So the exponential here is larger than the exponential here, because in this case we have that n is larger than m. So the limiting effect starts to make a relevant role, so that the growing organism tend to an asymptotic values of weight. Okay. Let's see this model from another point of view. Now we write that growth or increase in biomass, the m over the t is equal to h times m elevated to alpha minus k times m elevated to beta. In that case, for example, let's give a specific case. Let's analyze a specific case, a case in which, for example, alpha is larger than 0. Instead, beta is exactly equal to 1. In this case, we are in the case in which the second exponent is larger than the first exponent. So we are in a limited growth condition. In this case, depending on the value of the first exponent, so the exponent of growth, maybe 1/4, 1/2, 2/3, 3/4, and so on, we have completely different growth behaviors. I am employing these rational values, 1/4, 1/2, 2/3, 3/4, and so on, because these values of the exponential increasing part are somehow linked to some topological constraint related to the way in which resources are transported in living networks. We see some examples. Special case of the Ursi model is the von Bertalanffy model we have already seen when we were describing growth in bacterial population. In this case, in the case of von Bertalanffy model, we have the first exponent that is the 2/3 and the second exponent that is 1. We are in a case in which the second exponent, the exponent describing limitation, is larger than the first exponent, the exponent describing growth. Then we find from some experimental observation that a good or very diffuse values for calibrating these models when you deal with different organisms is that of putting the exponent equal to 2/3. 2/3 is 0.66. Several organisms that may be describing, whose growth may be describing by a Ursi model, more specifically by a von Bertalanffy special case of a Ursi model, may be calibrated by using a value of growth exponent equal to 0.66. Again, the assumption here is that the catabolism is proportional to the weight of a fish, so to the weight of the organisms, so that the negative decreasing part of the continuity equation is simply linearly proportional to the weight of the organism here. And the second assumption that may somehow justify the 2/3 exponent is that the area of the intestine proportional to the body is proportional to the body surface, and this proportionality may be described by a 2/3 exponent of the weight. Why this? Because the weight is a three-dimensional description of the dimension of the organism, while the area of the intestine that is available for absorbing metabolizable material is a quantity that is somehow described by a two-dimensional. This is why, from some kind of consideration we will look at shortly, some kind of ecological constraints consideration, we may say that the fact that the area of the intestine is proportional to the body surface ends up with the fact that the energy absorbed by a feeding organism is proportional to the 2/3 of the weight of the organism. This magic number 2/3 appears ubiquitously when we describe, for example, networks of distribution of resources. Again, this is a very general paradigm that is applicable to, for example, distribution of foods, so network for distributing foods, or distribution of other resources like water, so networks of aqueducts, for example, or even river networks. So these are networks describing, for example, the fact that water system, water bodies tend to distribute or to occupy the topological space with some kind of topological constraints. In general, we have indication that topological constraints in networks of distribution of resources tends to be well modeled by a limited growth model whose exponential part is in the range 2/3 to 3/4, while the second exponent, the exponent related to the limited growth limitation, is classically placed to 1. In this case, the indication that you may find, for example, in this paper that was published in Nature almost 20 years ago, is that the 3/4 exponent is valid for optimal networks, so networks in which the supply of resources is equal to the demand of resources. So this is an optimized network. So the 3/4 exponent is, if you want, the tendency of the evolutive tendency that somehow includes the second principle of thermodynamics for law of entropy and translate it into limited growth paradigm. In this case, you have that the exponent of 3/4 describes an optimal value in which your network is supplying in terms of what it is really required for life processes. In the cases in which you have a value of 2/3 instead, these are cases in which the supply is independent of the dimension of the organisms. So if you have an oversupply system, you will have an exponent of 2/3. If you have a perfectly balanced system, you will have an exponent with the optimal value of the 3/4. These are very theoretical considerations. I'm not asking you to understand them deeply, but if you like this reasoning, and if for some reason you would like to enter into the field of ecological theory, then you may read the article by Banavar and others that explains how supply demands conditions of network of resources distributions may produce different optimal settings for the systems in analysis. We finish the lecture of today by giving a quick look into the various models of population growth we have seen during the class. We have started by saying that linear growth, like the one represented by this first order differential equation, variation in times of the dimension is constant. This is linear growth. You know that in this case, the solution of this equation is a linearly growing system. We have said that in the case of, for example, bacterial growth, or in the case in which growth depends by the number of organisms growing itself, so you have a variation in type of the dimension of the system is proportional to the dimension of the system itself. In this case, we have a Malthusian exponential growth system. you know that the solution of this second differential equation is that x is proportional to an exponential, an increasing exponential of time. While in the first case, the case of linear growth, you will have that x is equal to time multiplied by the constant c. So x, in this case, the growth is linear. Second case, the growth is exponential. In general, as we have seen, you can embed in the coefficients of growth several aspects. In particular, we have seen that we can include the effect of temperature into this growth exponent, like, for example, including an exponential dependence on the temperature as seen as the difference from the optimal growth temperature, so the optimal growth rate. And then the solution of the equation of the logistic growth, that is the Malthusian exponential growth, on which you have a limiting effect. In this case, we may find a solution. This is the equation of the logistic growth. We have simply translated this Malthusian exponential growth by including the negative limiting effect of the carrying capacity. I recall you K is the carrying capacity of the system. In this case, we have limited growth, in which we have but the variation in time of the dimension of the system is equal to a growth coefficient times the dimension of the system itself, minus a non-linear, because this is a dependence of the square of the dimension of the system, but minus a non-linear dependence on the carrying capacity of the system. This equation may be solved analytically, and the analytical solution of this equation is what I have written here. So, if you plot this, you may expect that you will obtain a sigmoidal curve. So this is really the logistic growth, in which the growth is limited by the carrying capacity K. So K is the asymptotic value of the population or of the dimension X, while you have that the maximum growth rate is found at the semi-saturation capacity. You may recall from the chemical reaction models that we have seen, in particular the enzymatic reaction, in which we end up with the Michaelis-Menten function, in which the semi-saturation point, so the point at which the maximum, the growth rate is a half of its maximum possible value, is given by the half of the carrying capacity K. Okay, the very general solution of limited growth is that of sigmoidal curves. So please, you shall remember that unlimited growth is a biological nonsense. We cannot conceive that a system is growing unlimitedly. A living system, at least for a living system, it is not possible, for a simple reason that resources are limited. So the only significant or the only rational way of building or describing growth in nature or in biology or in ecological system is that of describing it as a limited process. Describing growth as a limited process bring us to a solution using URSI model-like solution, in which we have two terms, an additive term and a subtractive term, which both depends on exponential of the dimension of the system. The exponentials may be larger for the growing part or larger for the consuming part, so that if the exponents are larger for the growing part, then you have unlimited growth, so exponential growth, that is biological nonsense unless you consider this model applicable only on the early stages of development of organisms, because in the beginning, organisms tend to grow more rapidly. Then their ability to grow slows down, according to the fact, consistently with the fact that these organisms live into a surrounding environment that provides some limitations to grow. So you have a negative subtractive term. If you study the general solutions of this model, you end up with sigmoidal curves. So a very general solution has this kind of shape, this form, in which there is a dependence of coefficient A divided by this function, in which there is an exponential of a generic function of the growth rate. So this is a function depending on the parameter growth rate that may change in time according to the fact that the ability of these systems to grow may change in order to conform with the changing environmental conditions. So the sigmoidal, the very general description of limited growth is that of a sigmoidal curve, or in specific case, the logistic growth model that we have seen. In specific cases, for von Bertalanffy model, that is a particular case of a logistic growth model, and these are all particular cases of the more general model of Ursin that we have derived today by making some kind of assumption and analysis on the metabolic consumptions of the metabolic functions. Okay. Do you have any questions? We are quickly going to finish today. There are some other models that are important to look at least to know that these models exist, because all these models may be employed to describe very particular situation. A very well-known model is the Gompertz model, in which we start with an exponential Malthusian growth, and in which we make the growth rate depend exponentially on a function, on a coefficient that may be describing the mortality of the animal. So here you have a system of two differential equations. First, both are first-order differential equations, in which you may, the first one is exponential growth, the second one describes growth limitation by describing the fact that the growth rate R decreases exponentially as the population increases. So this is a way of including, of describing carrying capacity by saying that as the population increases, you have an exponential decrease in the growth rate. So as population increases, then the organisms forming the population starts to grow slowly and slowly, slower and slower. The solution of this model, again, is analytical solution. Derivative in time of a dimension is equal to growth rate R times the dimension times a non-linear function depending on the dimension that describes growth limitation. The solution of of this differential equation that comes out from the combination of these two equations is expressed here. Is this an exponential? It is, if you want, a sigmoidal curve in which growth is limited, but the sigmoidal curve shape is determined by the fact that you are describing mortality that grows exponentially with the population. So if you include an exponential decrease or an exponential increase of mortality with the population number, then you end up again with a sigmoidal curve that is much more pushed toward the left, and this means that the saturation values, or if you want the inflection point, so the point at which you have the maximum growth rate, arrives very quickly, very soon. So you have an inversion of a curve, of the concavity of a curve, that happens very soon due to the fact that the growth rate is decreasing exponentially with the population. There are other examples of these particular application of growth rate models. In this case, for example, we may assume that not all organisms, the offspring organisms are not immediately ready to duplicate themselves. Instead, we have to wait a time that we may call reproductive maturity. So you have to wait from the moment the organism born, then you have to wait for the organism to reach his reproductive maturity in order to replicate itself. In this case, you will obtain, again, a logistic growth, or if you want an asymptotic sigmoidal curve growth, in which you have some oscillations around the value. This is the so-called logistic with delay solution of the logistic of the delay, differently from the logistic. This is the logistics that goes to the carrying capacity. Instead, in the logistic with delay, you have a solution that may go over the carrying capacity, then you have a kind of oscillating behaviors with these oscillations that are damping with time, so that in the end, in the long time, you will always end to a carrying capacity of a population and for that system. Okay, we stop here for today. Do you have any questions?